All right, so when we were talking about the principle of work and energy before, when we were dealing with particles, do you remember I talked about two particular forces that we were really interested in because we had to deal with them over and over in a lot of dynamic systems or dynamical systems. Those two forces are gravity and spring, right? We are interested in the work done by gravity on any rigid body that we are dealing with, and the work done by springs, one spring or a group of springs uh, forming a rigid body system. So let's just review those. It's pretty much the same thing as we had when we were dealing with particles. It's just for as a reminder here. So work done by gravity, gravity force, uh, parentheses in because of the weight, right? Well, remember we had work from point 1 to point 2 because of gravity is basically minus mg delta h, and this delta h is change in height. Always keep in mind that this whole expression, work done by gravity, is negative if the height increases, and if it's positive if the height decreases. So always keep that in mind, and when we are calculating this delta h, make sure that you follow this rule. So negative if height increases, and is positive if height, well, this pen is really trying hard not to work, height decreases. Decreases. Right? So keep that in mind. The second type was spring, or work done by spring, better to say. So 2 is the work done by springs let's see if I can get this pen to do a better job. Springs, and that is, well, work done from point 1 to point 2 because of the spring is 1 over 2, well, it's minus 1 over 2, important, k s2 squared minus s1 squared. Here we said k is, well, here k is the spring stiffness. As I said, we defined this before when we were talking about principle of work and energy for particle or particles. Stiffness, and its unit is Newton per meter. It's very important about S1 and S2. It happens a lot that I've seen you guys making mistakes about this. S1 and S2 are the values of the stretch, or the amount the spring is stretched or compressed at the initial and the final position. So keep in mind, if you have the unstretched length of the spring and you know the length of the spring at the beginning, use those two to find how much the spring is stretched or compressed. If you know the unstretched length of the spring and you know the length of the spring at the end of the motion or the final position, use those two to calculate what is S2. So let me just write it here. Values of the springs stretch I have to write very slowly so the pen can catch up, stretch, or compression at the, this is very slow, at the initial and final position. The initial and final position. Right? It's very important. Keep that in mind. Don't just put the length of the spring or how much is the unstretched length. I'm just gonna do this one. The last thing before we start looking at the examples related to work and energy, how can we use it to analyze the motion, is talking a little bit about conservation of energy. The same story as we had for particles. When we don't have any non-conservative force, or all the forces which are doing work in our system are conservative forces, we can use conservation of energy, which pretty much says the kinetic energy, the sum of the kinetic energy and potential energy at any two positions, at any two positions during the motion, right, or is the same. So the sum doesn't change. Whatever you lose from kinetic energy, you gain in terms of potential energy, or the other way around. So what are conservative forces and what are non-conservative forces? Well, within the scope of our course, conservative forces are the forces I just introduced, right? Those particular forces, gravity and springs. Right? The work done by these two forces are the type of work that we consider as conservative work, right? Or the work done by conservative forces. Non-conservative forces, well, any external force applied to your system that is not these forces. Let's say you have some external force, 1000 Newton applied to your system, or a couple, in this case, since you're dealing with a rigid body, applied to your system, let's say 10 Newton meter, that's a non-conservative force, and friction. Right? Friction is also a non-conservative force. So if you don't have some random external force, which is not gravity or spring, or friction in your system, you can safely use the conservation of energy instead of using the principle of work and energy. So if I want to put it in words, I'll say if all of the forces that do work on a system of rigid bodies, that do work on a system of rigid bodies are conservative, the sum of the total, the sum of the total kinetic energy and potential energy and potential energy is the same at any two positions. Is the same at any two positions. Obviously during the motion. Right? Positions. Which means, well, T1 plus V1, V1 being the potential energy, T1 being the kinetic energy, is equal to T2 plus V2 at any 2 points. Now, Well, kinetic energy when we're dealing with rigid body, right? If it's a general planar motion, let's see, general motion, if you're dealing with that, well, T1 would be 1 over 2 mv1 squared, v1 being the velocity of center of gravity, 1 over 2 ig omega 1 squared. And T2, well, 1 over 2 mv2 squared, supposed to be squared, plus 1 over 2 ig, mass moment of inertia around center of gravity, supposed to be g omega 2 squared. Now for rotation about the fixed axis, right, if you have rotation about the fixed axis, right, what we get from here, well, as we said before, kinetic energy is pretty much is 1 over 2 I-O, let's say that's the axis of rotation, omega 1 squared, and T2 would be 1 over 2 I-O omega 2 squared. And for the potential energy, well, at point 1, let's say, well, conservative forces can either be, again, in all cases, can be gravity or spring. So the gravity would be mgh1, and this value can be positive or negative depending on whether you're above the datum or zero potential line that you choose, or below that. So if you're above is positive, if you're below is negative. 1 over 2k S1 squared, S1 being the same thing, how much the springs is stretched or compressed at the end, sorry, at point 1. Right, and V2 would be V2 due to gravity, which is mgh2. And again, keep in mind that this is S. I made a mistake there. Previous one, this is because of spring, right? So that should be S. S is equal to 1 over 2 K, like S2 squared. How much the springs are stretched or compressed at the end of the motion. And keep in mind that the gravity can be positive or negative, again, whether you're above or below the datum. You decide where the datum is and then go with that. So we're going to now look at a couple of examples, see how can we use principle of work and energy or conservation of energy, depending on whether we have conservative forces or not, and how can we implement these methods to analyze the motion of rigid bodies.